Hey guys! Alright, so today I'm going to teach you how to do an AP Physics C problem from 1985, and it's the third electricity problem, okay? Alright, let's start. A spatially uniform magnetic field B, perpendicular to the plane of the page, exists in a circular region of radius r equal to 0.75 meters, as shown above. A single wire loop of radius r is equal to 0.5 meters is placed concentrically in the magnetic fields and in the plane of the page. The magnetic field increases into the page at a constant rate of 60 teslas per second. Alright, so here is that picture. And here's my picture. I hope you can see it better. It's bigger. And you know, the X's mean that the magnetic field is going into the page. Alright, so for A they say determine the induced nth in the loop. Alright, so nth is going to be equal to d phi dt. Well, negative d phi dt. And d phi is the flux, and so d phi is also going to be equal to dBA, which is the magnetic field times the area, over dt. Like that. Alright, so we can break this up and leave the d with the b because we have a rate for the increasing magnetic field. So we can do dB dt times A. Alright, and so we have dB dt, and they gave that to us. It's 60 teslas per second, and we can find the area because we have the radius. So the radius of a circle is going to be equal to pi r squared. I mean, the area of a circle is going to be equal to pi r squared. So we can do 60 teslas per second times pi times r squared, and in this case, because we're talking about the on the ring, we use the inner radius, which is 0.5 meters. Get that. That's our equation. And all you have to do is plug it into a calculator, and we're going to get 47.12 volts. And then if we want to do sig figs, it's just going to be 47. There you go. So part A is done. 3 more parts to go. For B, they say, determine the magnitude and direction of the induced electric field at point P and indicate its direction on the diagram above. Alright, so we'll work on the magnitude first. So we know that V is going to be equal to ED, right? Okay, but we want to solve for E. So E is going to be equal to V divided by D. And we have the voltage because it's the nth that we just found above, and the distance is just going to be equal to the circumference because it's going around the circle. So when we plug, and the equation for circumference is 2 pi r. So when we plug that in, we're going to get 47 over 2 pi times, and again we're using the smaller radius because we're dealing with the inner circle, and we get 15 volts per meter. Okay? Alright. Now for the direction, because that's just the magnitude. Okay, so they give us that the magnetic field is increasing into the page, and that doesn't satisfy the induced electric field. So we want to increase out of the page. In increasing out of the page, using the right-hand rule, we realize that the current is moving counterclockwise. But the current is going to be driven by the electric field, and so the electric field is also moving counterclockwise. So when you're moving counterclockwise, we go this way, and at point P, it's headed towards the left, right? Alright, so at point P, there's my arrow on the diagram. At point P, the induced electric field is moving to the left. Alright. Now for part C. The wire loop is replaced by an evacuated donut-shaped glass tube within which a single electron orbits at a constant radius of 0.5 meters, when the spatially uniform magnetic field is constant at 10 to the minus 4 Tesla. C, they want us to determine the speed of the electron in this orbit. Alright, so they give us that it's a circular orbit, so you know that the force on the electron must be the centripetal force. So you set the centripetal force equal to the magnetic force. So it's mv squared over r, which is our centripetal force, is going to be equal to QVB. Like that. And so a V from each side cancels, and then we're going to rearrange to find the V. So we get V is equal to QBR over M. So we know the charge because it's an electron. We have the field because it's given to us, it's the constant, and then we have the R, which is also given to us, and we have the mass of an electron, which is 9.11 times 10 to the negative 31 kilograms. So all we have to do is plug in and solve. So the charge is 1.62 times 10 to the 19th. We have, I'm running out of room. Okay, so yeah, 1.602 times 10 to the negative 19th times 10 to the minus 4 Tesla times half a meter for the radius. Divide that by the mass of the electron. And for the velocity, we're going to get 8.8 times 10 to the 6th meters per second. There you go. So part C is now done. Last part. The magnetic field is now made to increase at a constant rate of 60 teslas per second as in parts A and B above. Determine the tangential acceleration of the electron at the instant the field begins to increase. Alright, so now we're going to go back to our good old friend, sum of the forces. So we know the sum of the forces is going to be equal to mass times acceleration. But the force here is going to be the electric force. So it's going to be equal to QE. Right there. Can you see? Alright. So from there we're going to solve for A, well the acceleration. And we get the acceleration is equal to the charge times the electric field divided by the mass. That's just rearranging the equation. So again, we have our charge, we found our electric field, and we know the mass of the electron. So when you do that out, you're 1.602 times 10 to the negative 19 coulombs for the charge, 15 volts per meter, because that's what we found in part B, all over, again, 9.11 times 10 to the negative 31 kilograms. And our answer is 2.63 times 10 to the 12th meters per second squared. So there is our acceleration. Okay? Alright, so we're done with this problem. If you have any questions, feel free to ask me. If not, have a great day. Bye.